V.Shende? Yeah. So axiomization of the lab Fukaya category.
Thanks. So, in Maxime's first talk in this conference, he wrote Fukaya category and then said this is something very complicated. But once upon a time, homology was also something very complicated. You would have to discuss simplices or forms or covers or something, had some construction, had many constructions. And then Allenberg and Steenrod wrote these axioms. And after they wrote these axioms, we all know what homology is. It fits on this blackboard. There's one more axiom which tells you the homology of a point, which I didn't write. It's because this is conference on coefficients. So I want to present today something similar to the wrap Fukaya category in the exact case. And I put these axioms up here for comparison.
Actually, it's easy, but it's kind of difficult result, and you can see infinity structure of almost spectrum.
Yes.
No. This axiomatics, this looks kind of neat, but in fact, it's kind of tricky result.
Yeah. The same will be true about what I But before getting into that, I want to give some sort of reminder for those people who are not been studying the skeleton and sectors and so on, why we want these sectors in the first place. So this is just a sort of brief motivation. And so there's one example I always like to give, so I apologize if you've seen it before, but it has to do with the mirror symmetry between the projective line and whatever it's supposed to be mirrored to. So let me in fact begin with a simpler mirror symmetry between C star, the SYZ fibration goes over the line. And as we all know, this is mirrored to the cotangent bundle of S1. What I want to, so let me just draw this C star. Okay, it's me drawing like a cylinder. And this S1, C star S1 is also a cylinder. And now I want to compactify this C star to P1. Okay, so I'll replace this by P1 and cap it off. And if you listen to what SYZ tell you, or what the physicists say, they'll tell you that these circles, they've shrunk to 0 size here. So on the mirror dual, they should expand to infinite size. Now in mathematics, it's not so good to discuss circle of infinite size. So you need some way of making sense of it. And one way of making sense of circle of infinite size is you can't go all the way around. Okay, so the way we make sense of it is we say that we should do something where we declare, by whichever method you like, that we don't go all the way around. So I will do that by just recording the fact that you cannot go past this grid. And the reason this is a good stop. It's stop, yeah, it's called stop. Now the reason this is a good idea. Okay. So now let me take 3 P1s. Now this is something that fibers over the circle. And on the other side, well, I at 3 points degenerated a fiber to 0 size. So now I should have a torus with 3 holes. But I want to draw this again. Torus with 3 holes. maybe it would be better if I draw them like this. Okay. Here's torus with 3 holes.
It's just for education. It's the same picture, right?
It's the same picture. Yeah. And you know, if you Dennis is here, so if you ask Dennis how you compute category of coherent sheaves on this item, he might tell you one of 2 things. Option 1, he might tell you that it's the colimit of coherent sheaves. I'm not going to write coherent sheaves for each of these things because I'd have to write it 9 times. Of the coherent sheaves on this diagram. That's like what int code takes push-outs to push-outs. But there's a different thing he also might tell you, which is that if I cover this, there's a different cover of this, which I want to mention because it's something Denise said yesterday. You can cover it like this. And you can take a limit. Of the coherent sheaf categories here. And just to clear up a misconception that somehow has become very widespread, whatever I'm doing with Sheil and John has to do with this and not this. These are mirrored to 2 different things, and I want to discuss that one. Okay, so on this picture.
So what are the dots there?
Punctures?
Oh,
This is the point where
I thought, this is
the
a
point where
This is a
you-
point.
you want.
it's a point.
It's a point.
intersection points.
So I want to draw a picture here. And I had, okay, so I'm going to draw it. And the thing which I'd like you to observe is that if you look at this shaded red region here, it is exactly that cylinder, including these green boundaries. And so I've taken 3 things that are mirrored to P1 and glued them along 3 strips like this.
With boundary, the Lagrangian can stop some here. And, draw a typical Lagrangian, which you can see.
So
It's not clear.
yeah, if you want to, I should say in this talk there will be no Lagrangians, but the sort of Lagrangian you consider looks like this. It does not, Lagrangian never, one does not discuss Lagrangians which go to the stop. Okay, so what you learn from this picture is that if you have a, if you can make sense of the Fukaya category of this kind of sector,
What just like we
let me just draw a picture.
You call those strips the stop, but the stop is the holes, right?
No,
No, it's also,
the holes are the infinite boundary.
you're allowed to go to holes.
The holes are the
Yeah, the holes are the infinite boundary. And you see in this picture, there's this piece here, and I've glued the hole together out of 2 of those. Well, the holes are the infinite boundary. Anyway, so the point is, if you can construct a Fukaya category, which is covariantly functorial under this kind of inclusion of this green strip into this one or that one, such that it takes gluings to colimits, then you can reduce proving mirror symmetry for for things of this kind down to mirror symmetry for toric varieties. So that's one motivation for this discussion of sectors and skeleton and so on. Okay. So that was this motivation. Now I want to write the axioms. Maybe I'll take it out of this whole board.
In terms of skeleton, just embed real line to real line plus.
Yeah, maybe I should draw a skeleton.
Yeah.
I'll draw a skeleton. The skeleton would look like this. But in this talk, there will also be not so much more skeleton. Now, it's axioms. Turn it around. So first of all, I want to be given the data of a functor from sectors, so Liouville sectors.
Not Weinstein.
Well, like in homology,
Yeah.
this is defined on all topological spaces, but these axioms only characterize it for CW complexes.
Yeah.
So here, I may as well, you could restrict to Weinstein if you want, but it will only characterize it for Weinstein.
Okay.
To some form of stable categories. And I'm also going to ask for the data of a natural transformation from this functor to this functor applied to whatever times the cotangent bundle of the interval. The cotangent bundle of the interval plays a special role in this theory. So this is the data.
So stable means the usual stability thing.
Stable means stable infinity or A infinity or DG. Your choice of model for stable.
It's not
category.
stability, not Bridgen stability.
Yeah, different kind of stable. Different kind of stable. It's like topologist stable. Sorry, DG.
How do you think of these things in this slide?
What?
With a minimum or maximum? You don't care.
No,
these
close
ones are
interval,
one.
close interval, yeah.
So for me, the only information.
Object will be what?
The only question you're allowed to ask me is what is the Liouville field? And I will, so let me draw the Liouville field. It's this one. So that Liouville sector. Answer?
Yes.
Okay.
There should be equivalence, yeah. It's natural.
These are
I will
data,
put
then
in,
there will be
so in the end it should be equivalence, but I don't want to put that directly in the axioms. I want to put some weaker form of that
Okay.
and then conclude that it's an equivalence for Weinstein things. Because in particular, I don't know this is I don't know a proof that that's an equivalence for any Liouville manifold, and I don't even necessarily believe it's true. Because you might believe that this contains more objects.
Okay.
I'm going to put in the axioms that it's fully faithful, and that I know is
Okay,
true.
okay.
But it's not subjective. I don't. So. This is data. Vectorize the properties.
Basically, this dot means point or any.
No,
Anything.
Okay.
The dot is everything.
So embeddings in equal dimension and inclusion which increase dimension. Yeah.
That's right. Yeah, that's right.
Little sectors kind of like inclusions of dimensions. Yeah.
Yeah, that's right. That's right. Maybe I should remind. So now, inclusion of Liouville sector. It's inclusion of the symplectic manifolds, which is proper in the topological sense, carrying the infinite boundary to the infinite boundary. And let me just, rather than write it in the axioms, I'll just demand already that this is fully faithful.
So, can you explain what are the extra objects that you would expect to see in the Liouville but non-Weisstein case?
No, I'm just saying that, like, what do you have to prove to say that this is surjective? You have to get some control of what kind of Lagrangians you can find in here. And the way I'm going to prove that in the Weinstein case is because I know generation for Weinstein manifolds. And so I know what all the objects are here. And I can argue they're all cocores, so they all come from this guy. But in the Liouville case, I don't know any such generation result. And you can imagine that there's some objects here that are represented by Lagrangians that cannot possibly come from this thing. You could imagine. And so for instance, this might be a way of showing that some Liouville manifold can't be deformed to a Weinstein manifold.
Even if topologically it's plausible. You mean?
Yeah. I don't know any example, of course, but could be. Okay, so the properties. So the first property I'm going to demand is that this natural transformation, when I put t star 0, 1 to some power, this is an isomorphism. I would like to ask that maybe I should call this one 0, which is that isotopies of inclusions isotopy of inclusion goes to equivalent maps. Let me say in a precise way, because I don't need this. So an inclusion isotopic to the identity. Inclusions isotopic to symplectomorphisms. This goes to an isomorphism. At 2.
In point 1, can n be 0?
Yes. The most important case.
Yeah, but in fact, the suggestion you can maybe redefine Fukaya critical by stabilization by adding.
Yeah, you could do that,
Yeah.
but then you would lose this thing that I've said might be true. That maybe you could use something to detect the difference between Liouville and Weinstein
Yeah.
by the failure of the stabilization.
Yes.
That's
Yeah, it's for some topological case. Yes.
Yeah, yeah.
Interpretation.
But yeah, you could of course just define by stabilization.
The category is linear in a ground field or
Integer? I think some integer should be.
It should be even over sphere.
Over spectra, yeah.
I don't specify yet. Later on, I'm going to restrict myself to like 2 periodic Z mod 2 coefficients for a reason I'll explain.
Do you don't assume that the isotopy itself induces the isomorphism? Just that there isn't.
No. This functor W is a functor. It will send an inclusion to something. And so I assume that if the inclusion of
I'm asking for coherence with the isotopy.
I did not impose that.
Okay.
But I mean, like you know, if you have an inclusion and another inclusion, which combines to this inclusion, the fact that this is a functor says that this diagram should be coherent. So somehow
It's maybe
we could approximate
can
that.
be used by this. Maybe. Yeah.
It just tells you you get an isomorph.
Yeah, but if you have 2 of them, you wouldn't get the same as
Maybe just step by step you can embed back and forth.
Yeah, you can include and then include, and it's not, you can approximate the isotopy, but it's not including. Okay, so 2 is that fully stopped inclusions. I'll explain what this is. go to fully faithful morphisms. 3 is that if I have x, y subsectors of z, and so I'm going to have to explain some terms, and so I'm going to outline that. If I have subsectors of z, and x is what I'm going to call not in front of y,
So
this
what
requires-
is a sector?
this requires.
What is the meaning of sector?
Stops, yeah.
I mean, in Scheele's talk, you define the Liouville sector. So X is the Liouville sector is Liouville manifold. It's like Liouville manifold. It has boundary, and along the boundary, there's some condition about the boundary that's. I'll review in a little bit. If X is not in front of Y, then in Z of anything from. Okay, I'm probably going to get the direction wrong, but I'll correct it later. It's some sort of orthogonality condition.
in W or Z?
In Z.
No, in W.
Double,
is a category.
This is spaces, yeah.
In W of Z.
And double.
Y acts as 0 for
No.
Y in the image of W of Y and X in the image of WX. Okay, so these are, then there's one more axiom. And this one is the hardest to state, so I've saved a blackboard for it. So 4 is the axiom of stop removal. And this says the following thing. So so given Liouville pair, Z X. So this means X is in the contact boundary of Z, and a subdomain X prime of X, Liouville subdomain. So just a fact about Liouville sectors is that there's a morphism of sectors from Z minus X. So Z minus X I've removed more, so it includes in a thing where I've removed less. So there's a morphism of such sectors. And I demand this is a functor, so there's a map like this. So the axiom of stop removal concerns this map. So given a Liouville pair like this and a subdomain like this, such that the skeleton of X intersect X minus X prime is Lagrangian. If X is Weinstein, this is automatic. So as Scheele was explaining in his talk, when you have a Legendrian, for example, the Lagrangian skeleton of this subdomain of the contact boundary included in the contact boundary, then there's a linking sphere to the Legendrian. And this is also a Legendrian, and it's fillable by a linking disk. So this is a linking sphere. And it's fillable by linking disk. But I don't want to discuss Lagrangians in these axioms, so let me observe that always, if I have an exact, if I have a Lagrangian disk, it lives as the fiber of a sector like this. Okay, so there's two. You should think a little bit carefully. So if you have a symplectic manifold if you have an exact symplectic manifold in general, it will not define a sector in its neighborhood. Because, how to say? So the point is that when I say this disk defines a sector, this is my linking disk, not the zero section. So whenever you have a disk, you can thicken it up in this way to a sector. So, and this is the definition of what's called linking sector.
Excuse me.
Just 1 second. So these linking sectors, they sit here, and the statement is that this sequence is exact. That this is a quotient of this by that.
Yeah, just
Okay.
I'm a bit confused with it. What is the definition of skeleton here? I don't know.
It's the locus.
I think you're too late. As a forecast.
Well, I can define it. You know, a Liouville manifold has Liouville flow. You look at the locus, which does not escape under the Liouville flow. Okay, so here are the axioms. And I owe you definitions of fully stopped and not in front of. So let me write those here. So fully stopped. So this means that okay, so I have to draw sort of a picture. So
Excuse me. So it means that independently of those actions, you have a definition of linking sectors for any such situation where x prime is in X. And
so the definition of linking sector is you take the linking disk. You remember the definition of linking disk? It's I take this linking sphere and I fill it, which I can always do because the linking sphere is small. And so linking sector is I make this construction. And it's if you think a little bit, you'll see it's a subsector of the complement.
Still zero satisfies something. Zero.
Yeah, I haven't put the point axiom yet.
Yeah.
So well, let me write it later. So fully stopped means, so if I have an inclusion of sectors x and y, then the boundary at infinity of x, it splits into somehow 3 pieces. There's the part of the boundary when the wave flow is entering, the part where it's exiting, and then the part where it's somehow just traveling along. So, I call those the in boundary, the out boundary, and the trivial boundary. And fully stopped means there exists, so this is the definition of fully stopped, there exists an embedding of the contactization of the, let's say, outward going so this is the contactization of the outward going boundary into the boundary of infinity of y, with one end of this going, so with this one end of it going to this original thing, and the other end going to the out boundary of y as a subdomain. So as a subdomain. So that's the precise definition of fully stopped, but intuitively what it means is that the outgoing boundary of x, you can just flow it into the outgoing boundary of y. And the reason why you should expect this axiom to be true is that, well, if you're computing wrapped flow homology in x, it means you wrap in x. And what this axiom says is that somehow wrapping in y is not very different. You just somehow, it's a little bit different at infinity, and you just never change anything. So that's the definition of fully stopped. And now I want to give the definition of not in front of. The definition of not in front of is similar.
So you mean symplectization? Embedding of symplectization?
No, contactization.
The boundary.
Boundary out. So X is a symplectic manifold. Boundary at infinity of X is contact manifold.
Yes, so you want
The boundary. Yeah, sorry. I didn't put enough of these. This is the boundary of the boundary at infinity of X.
Yeah, now it makes sense.
Okay, good, sorry.
Okay. Can you draw a picture more?
I'll draw many pictures in a little bit. The whole point is to calculate some examples using these axioms, but I have to first finish writing the axiom. Okay, so then I would like to explain what is not in front of. So, not in front of. So not in front of, maybe I'll just say it in words. It means that for X to be not in front of Y means I can embed the analogous thing for, I guess, Y without meeting X. But I don't demand that it go all the way to the contact boundary of the ambient thing. But you have to embed it in a way, so, like, this has infinite length, and you have to embed it in a way preserving that infinite length. And it doesn't have to be an embedding, it has to be contactomorphous. Okay, so that's what I wanted to say about these axioms, and now I want to explain why they characterize this kind of.
No, you should have a point, yeah.
Yeah, point axiom. So,
what?
two periodic Z mod 2 modules.
Okay.
I'll explain why two periodic, but I will not explain why Z mod 2 modules.
Z2? Z mod 2?
So okay, let me just write this. So, as it stands, I'll just write this for now. So the point is two periodic Z mod 2 modules.
Can you write point instead of a dot, because you have dot subspace?
And you'll see from a calculation I'll make that two periodic is actually forced upon me, but Z mod 2 modules maybe it's not.
I just don't want to care about orientations. Are you lazy?
No.
No.
Why Z mod 2? Yeah.
Because Z mod 2 is somehow the Z mod 2 module Z mod 2 has the property, it has a unique automorphism. And so, like, it will happen that there's some automorphism I have to pin down, and I don't have an argument to pin it down. And it gets pinned down by
it was a
being-
convenience to prove theorems here, but in real life.
No, of course, yeah, it could be something else. But two periodic, you have no choice.
Yeah, okay, yeah, because you don't want to care about spins or whatever.
Yeah, unless you put additional structures, you're stuck with two periodic, and I'll explain more. But the thing I want you to observe about these axioms, not only is there no discussion of holomorphic disk, there's no discussion of Lagrangian.
What is Lagrangian?
Sorry?
The skeleton, yeah.
Oh,
Yeah,
in the skeleton.
secretly,
Yeah,
secretly.
okay, in the skeleton, yeah. I think we can formulate this without Lagrangian.
I just add disks, yeah. So
Yeah, you can like discuss how the pairing's supposed to work. Well, secretly there's Lagrangian in the disk. So let me explain what you can learn from these axioms. Oh, but maybe even before that, it's important to say.
You didn't explain that before.
Yeah, I explained it. I'll explain it again. I didn't write it. Not in front of means you can do this kind of embedding without meeting the other guy. But it doesn't have to be embedding. It can like wrap around, but it just has to avoid the other person.
So are you claiming it's a theorem that if you have one of these, that all of these are all the same?
Let me state. Let me state now two theorems. Okay, so theorem, and this is from GPS 1 and 2. So GPS 1 exists. GPS 2 also exists, but hasn't been posted yet. Such a category exists. So theorem, and this is in GPS 3 and 4, which do not exist. And is needed. But I will explain somehow why this is true.
There's a no problem with multiple covers and rational denominators and all this. Yeah.
Sieht man too much.
No, in general, but in the symplectic topology business.
Everything is exact, right?
Yeah, everything is exact.
Exactly. Yeah, there's no cover.
Yeah, it's exact case.
Yeah, but then the people constructed spectra, everything in spectrum, not in groups.
Yeah, then
Yeah, categories.
Maybe we discuss later.
Okay.
But I want to explain why this is unique, because maybe some time before this GPS 3 and 4 appear.
So for example, if this if W is zero, non-zero implies there is some Lagrange sum manifold based on trivial free homology.
A posteriori, yes. Yeah. Direct argument, I don't know.
Okay. Yeah.
So-
But yeah, using these two theorems.
Yeah, using these two theorems,
Okay,
yes, that's
understand.
about it.
And so, where do you assume Weitstein in those two theorems?
Oh, sorry. The theorem. Yeah, this theorem says now its value on Weinstein manifolds. Its restriction to Weinstein manifolds. Yeah, thanks. So let me start to explain how these axioms tell you anything at all. So in Scheele's talk, if you sort of remember it, you will observe that the only ingredients in the generation argument were these axioms. Okay, so from Scheele's talk. That for Ax Weinstein, that if I take the Kokoi sectors, and this is surjective. So but same argument next time. So I'd like to explain now. I'd like to explain now gluing. Okay, so gluing. So like before, we had this at the beginning of this talk. There was this picture where there was something happening on one side, and I wanted to glue along something, and something happening on the other side. And that was just a picture in the two-dimensional case. But let me have a picture in general. So I'll write precise statement. So let X be a Weinstein sector. And Y and X a Weinstein subset. And then I will deduce from these axioms that the wrap category of X is the wrap category of is a push out. Full limit of the a wrap category of X of Y with a wrap category of X minus Y. So if you think about what the definition of sector is, the complement of a sector is always a sector. So this makes sense. And it's a push out over, well, if you remember the definition of a sector, along the boundary of a sector, it should be trivialized with the fiber a Liouville domain one smaller. So in here is something called W of F, strictly speaking, times T star 0, 1. And let me explain the proof of this theorem. So someone asked to recall what is sector. Now, one way to define sector is to say that, so the definition of sector is that near the boundary, there exists symplectic vibration from X to a half plane. And that's what it means to be sector. And then the boundary goes over the half plane. Okay, so let's draw that picture for the subsector Y of X. So here is the half plane, and Y is fibering over the half plane. And the fiber of the fibration over this line, so the fiber over here is F. That's what that F is. So the way you prove this theorem is you first construct a new sector. You say, okay, I'm free if I want to add more stops. So I add more stops. And the virtue of adding these stops is that if I look at this F times T star 0, 1 sector, now the inclusion is fully stopped. Because this is the right direction, and it runs right into these new stops. These new stops, by definition, are just deleting F here. So that lets me appeal to axiom 2 and learn that in this new item, the inclusion of F is fully faithful. And similarly, I can learn that the inclusion of this and this, this are fully faithful. So I have the following situation. I want to show that this diagram is a push-up. This W of Y, W of X, W of X minus Y is a push-up. What I will in fact show is that this diagram is a push-up. So you'll see that what I've done is I've taken X minus Y and added a stop. So let's call this X minus Y with some additional stop added. And then also I've added a stop on Y. Okay, so I'm going to prove this, and then this, this pushes out to W this whole thing. So this is W of X with 2 stops. And so this is what I want to prove. I claim that by proving this is a push-out, it proves this is a push-out. And this is just some sort of formal fact about categories, because these are quotients, and this one is a quotient by the image of what I took the quotients of from these two. So it's enough to prove this one. But the point is that if you look here, the inclusion of W of F into this stopped guy was fully faithful. And if you think a little bit more carefully, by the generation argument, in fact, the orthogonal complement to the inclusion comes from comes from this side. Right? I mean, I explained that this thing is generated by co-core sectors, and by this generation argument, all the linking sectors here can be expressed in terms of somehow images of the co-core sectors here and the co-core sectors there. So that explains that, in fact, the category on this side, I guess I called it Y stopped, has a semi-orthogonal decomposition with one piece coming from F and the other piece coming from the somehow X minus Y minus F. And likewise, this side also has a semi-orthogonal decomposition, and by the same argument, the whole thing has a semi-orthogonal decomposition into just this piece and everything else. By a combination of this somehow stoppedness of being fully faithful and the generation argument. But when you have a diagram of categories of this form, where you have some category C, and then here you have some semi-orthogonal decomposition CD, and here you have CE, and here you have CE plus D. This is a push-up. That's just a fact. That's a fact about categories.
Yeah,
So,
yeah, but in fact, I found it the offensive, this language of simplective topology. If you speak about skeletons, the things are twice less dimensions, much easier to draw, and you just draw infinite ray up and infinite ray down. Yeah, this business. You get kind of transversal interval.
so one reason I prefer.
It's just the same. Yeah.
Yeah, so argument is the same, but one reason I prefer this
because
picture is that it applies to all skeleton at once.
Yeah.
I didn't discuss skeleton at this point.
Yeah, no, but in principle, just decompose the whole thing as a product of interval to let to this interval things.
Yeah, that's
goes
right.
up and down. Yeah.
Okay, so that's this gluing. Yeah.
So, do you expect this to fail in the general UV case?
So, I mean, I don't know if I expect it to fail, but it was essential in this argument that I knew generation. I mean, the thing that's always true is that this piece here is orthogonal to anything that comes from there. But what's not obvious is that this whole side is generated by stuff from here and stuff from there. The only way I knew how to prove that is by first proving the full generation result. And it seems like overkill, but I don't know how to do that. So, yeah. So that's this localization argument. Now you could ask, I mean, it might be reasonable to ask, given the localization argument can almost be drawn in one picture, why don't we write it? This part of the localization argument is not so hard. The thing that's difficult is not. Let me illustrate a slightly problematic fact about sectors. So here's a disk. Here's one subsector of a disk. I should distinguish the kinds of boundary. Here's one subsector of a disk. And here's another subsector of a disk. So the problem is their intersection is not a sector. So sectors, as exactly as in Frano's talk, sectors do not form a Grothendieck topology. So the real difficulty in showing this localization is showing that you can give a cover by sectors for which all overlaps are again sectors. So that's the real content of GPS3. So GPS3 is the statement that a given A, and there are some assumptions, cover of the skeleton, A cover of the skeleton lifts to a cover by sectors all intersections and unions of which are sectors. So once you know this fact, then you can apply this somehow push-out argument to convince yourself that the thing localizes over the skeleton. But you somehow you need to know this fact, which is slightly annoying to prove. But still, at the very end of the day, that tells you that your category localizes at the skeleton, but it doesn't tell you anything about what that category is yet. So finally, I would like to explain how you ever compute anything. The key calculation is the calculation for the three-pointed disk. So I have a disk. Three stops. And the way you calculate for this three-pointed disk is you observe that, first of all, you can include it in three different ways into a cotangent bundle of an interval. And also, there are three inclusions of a cotangent bundle of an interval into this strip with three boundaries. Okay, so let me call these three small strips A, B, and C. So I claim, claim the wrapped category of the, I mean, you know what the answer has to be. I claim the wrapped category associated to this thing is the modules with the appropriate coefficients of the A2 equivalent. I want to somehow explain the proof of this from the axioms. So the first thing to observe, lemma, the wrapped category of the half disk is 0. And proof, I can include into this half disk, well, I guess I'm drawing the wrong one, whatever, this is the stop boundary. I can include the following two half disks into this half disk. And this one is not in front of this one. And one of them is not in front of the other one. So harms from in one direction from one to the other are 0. On the other hand, both of these inclusions are isotopic to the identity, to a symplectomorphism. So you're okay. So this is the proof. Did it make sense? Yeah. The categories.
So they're talking about the composition of two copies of the category of representations of K. That's what I'm saying. And the gradient factor is the identity, which is this.
Yeah. But this is 0. Yes. Yeah. So first you need to know this. What? Then observe that by the stop removal axiom, when I take the quotient by the image of this strip, I'm left with the category. So let's write it. So that's this lemma. And now I observe that if I have C and I include it So this is what the stop removal axiom says. It says the following sequence is going to be exact. So it's a C, A, B, A, B, 0. So the quotient by the image of C is this string. Or likewise, the quotient by the images of both A and B would be a half disk. So you see, even if you hadn't seen from the general generation argument, that this category is generated by the images of A and B. So that's pretty close to showing that it's modules of A2 quiver. What is missing is I should show, first of all, that there are no harms in one direction, and that I should then compute a certain bimodule. So we learned, we saw that this thing is generated by A and B. And by the way, you can see that the inclusions of A and B are both fully stopped because they get stuck. So the inclusions of which are fully stopped. And A is not in front of B because the right direction is like this. And so I can flow B as much as it can go without ever hitting A. So using my axioms, I learned that this category associated to this thing, it has a semi-orthogonal decomposition into the wrap, two copies of the wrap category of this guy. And there's one last thing to compute about what is harm from someone in here to someone in there. So let me just say how to compute that. So I look at the image. So let me write 1 for the true periodic Z mod 2 module, which is Z mod 2 in degree 0. So I look at the image of 1 from C, and I ask, where does it go? Now, when I take so because A and B generate, this is something in A, the cone on something in A to something in B. And it has to be cone in that direction because there's only morphisms in that direction. Now, if I take the quotient by B, then the inclusions of A and C are both somehow isomorphic to the identity. And so you learn that this has to be a cone. So if I take the quotient by B, this becomes an isomorphism. Therefore, this had better be 1A. This had better be 1B. And so the only thing that remains is to calculate this map. And so the point is, I calculate it in the wrap category of this tripod. It's harm to itself. And well, this harm, there's the part from A, the part from B, and then the part that I'm interested in. So this is harm 1A, 1A, plus harm 1B, 1B, to harm. And this is the thing I'm trying to compute. Harm is wrap category of this 1A, 1B. On the other hand, the inclusion of C was fully faithful because it was fully stopped. So this whole harm is isomorphic to Z mod 2. And also on this side, here we have Z mod 2, Z mod 2, and some mystery, so the mystery is also Z mod 2. Okay, so that finishes the calculation. And it's 2 periodic Z mod 2 modules. So now let me say briefly, I mean, it's modules over that quicker. So now let me say briefly, because I'm somehow 2 minutes over time already, how you finish this argument and prove that this characterizes everything. So once you've calculated this, this particular gadget, then you've in fact calculated the wrapped category of the following pair. Take any plumbing of cotangent bundles of spheres in a tree. And then take the Lefschetz vibration, which kills all spheres. Now, when you try and, it follows directly from the axioms that somehow thimbles generate. And when you try and calculate Halms between the thimbles, every time the only way they ever intersect is in this configuration. Because that's how sort of spheres intersect in the plumbing of spheres. So from this calculation, you learn how to calculate all this example, this tree plumbing of spheres killed by the Lefschetz vibration. Now it's a fact that this tree plumbing of spheres, then trivialized, that pair is, you can construct an isotopy between it and the link of the arboreal singularity. And I'll just draw one picture explaining why this is true. So in Tobias' talk, we saw somehow this link of the arboreal singularity, and then the isotopy, you just slide this one down there, and it looks like this. This is plumbing of spheres. Yeah, it goes on quickly. Now, then from the localization argument, you learn that everything is determined by, you can deform to the case where your skeletons are arboreal, covered with this kind of stuff, and we've calculated now all of this kind of stuff from the axioms. So you learn that you have a sheaf of categories, a co-sheaf of categories in the skeleton whose values you know at every point, and then you're left with a mystery of, well, maybe there's some twisting. But I've forbidden any twisting in my assumption of coefficients. If I take 2 periodic Z mod 2 modules, then there's no room to twist in this co-sheaf.
So you have a Q or something, then that's not phase.
Yeah, then there could be some twisting. And then you need to somehow specify additional data to pin it down. Maybe I'll say one last thing, which is that another thing which follows directly from these axioms is if you consider any symplectic vibration over a 2-dimensional base, and you look at pre-images of sectors in the base, and look at their values, that defines exactly the kind of thing that Kapranov was describing in his talk. So it's immediate from these axioms that you somehow, symplectic vibration gives you Schober. Okay, so I'll stop there.
Thank you very much. Any questions? So if you try to go beyond this Einstein cases,
Yeah.
then suppose the UV case, for example, you consider kind of category generated by embedded exact range and something more general, like immersed, and then kind of, if they are really different, it means that this uniqueness fails, sort of thing.
Yeah, I think so. Yeah, yeah. What this? I mean, immersed will I think be the same as if you do this thing Maxime was saying, it's just defined by stabilization.
Yeah.
Then immersed embedded doesn't matter.
Yeah.
But maybe it's some more general objects than that.
Yeah, I mean, so this generating kind of ensures that kind of thing does not happen in the mind.
Yeah, that's right.
Okay. Any more questions? Okay, thank you very much.